All right, let's quickly get through the problems that I wrote on the board last time about error between curves. Bounded by sine x and x-axis on 0 pi. So basically the idea here is you have our sine graph doing its thing. And 0 is here, pi would be here. So this is the sine graph. And this is the x-axis. And so between 0 and pi, I'm talking about this area right here. How do we find that area? How do you compute the area?
The integral of sine from 0 to pi.
Right. So that's pretty much an area under the curve problem. Integrate sine, you get minus cosine. Cosine of pi is minus 1. Minus cosine of 0 is 1. So the area is 2. Okay, what about so you're told that you're not given any limits, which is of course possible. So here we told you what interval we cared about. Here you aren't. You just want the region bounded by these two. Probably what you want to do is graph it. So you have a good picture of what's going on. Y equals x squared, we look like that. Y equals radical x, we know looks like that. And so the region between them will of course be this guy. So I know I want to integrate over the interval that bounds the shaded region. It's a very important idea. See multivariable calculus, something like that is important. Knowing how to actually sketch a region and bound it on an interval. How would we find the bounds? Or the limits of the integral, as we call them. How would you actually do that? Because we know the area is going to be, but what is the area? It's going to be the integral of something, integral from a to b, where our a is going to be here, b is going to be here. How do I find a and b?
It's the top minus the bottom. Oh, that's not what you're saying.
Yeah, how do I find a and b?
It's when x squared equals the square root of x.
Find the intersection. Where these guys give you the same value. You can see by inspection that 0 and 1 are going to be the answers. If you don't see that right away, we could square both sides. Then I could bring the x on that side, I could factor. And so I get x equals 0 or x equals 1. The other two roots of that would be actually complex roots. So I know this should be 0, that should be 1, and we are all going to integrate top minus bottom. We'll integrate top minus bottom. Or right minus left, depends on the context. And so ultimately we have to integrate 0 to 1 of the top curve, which in this case you can see is the square root function. That's on top, right? Imagine you're a little man trapped in the shaded region. If you look up, who are you seeing? The square root. Minus, if you look down, who are you seeing? Well, x squared. So that's what we have to do. So this guy is x to the 1/2, add 1 to the power, you get 3 halves, divide by the new power, you get 2/3. This gives you x cubed over 3 between 0 and 1. That gives you 2/3 minus 1/3, which gives you 1/3. Third example. It's like a strange one. Area under this. Okay, so we know the roots of this one would be 0 plus or minus 2. So we'll pass through here, pass through minus 2, pass through positive 2. It'll be a cube graph, so we know that the right side goes up, the left side goes down. Plug in a number in here. This is x times x minus 2 times x plus 2. So if I plug in, say, minus 1, negative times positive, that's positive. The graph is up here. Plug in, say, positive 1. Positive times negative times positive, that graph is down here. So our picture looks like this. And of course, between minus 2 and 0, means we're looking for this guy. No surprise here. A would be integral from minus 2 to 0 of that function. Quickest way to do this is to just expand. Which, if you guys looked at the solutions to the last quiz, I think it was the first problem, the first integral problem. The easiest way to do it by far was to just expand and use the power rule, but I had a lot of people trying to force a substitution in there, and they're trying all kinds of maneuvers to get somehow, I need to call something u. No, this is never the strategy. You always try the simplest way out of a problem. You don't think substitution first, you think power rule first. You think, can I expand this or simplify it to look like the power rule? That's always going to be the first line of defense. Substitution is the second thing you think about. So don't think you have to force a substitution somewhere. Just think simply. Think as simple as possible. Right? And I actually wrote out the solutions to both because I saw several students trying to do that, trying to get a substitution for the first problem, and it was night and day. Like, it was a one-line problem, and when I did it with substitution, it took up 3/4 of a page to just like actually write everything out and figure out how everything fits in. Think simply. Math is hard enough, you don't have to make it harder. You always go for the simplest thing first. Get the low-hanging fruit. Before you think substitution, think power rule. You always think of the basic rules first. Is there a way for me to rewrite this to use a basic rule? Is always your first thought. So you see something like this, so I'm like, oh, I can do a substitution. U equals x squared plus this, and then substitution, I'll get the x here. It's overkill. Just expand. can use the power rule. Of course, if I plug in 0, it's 0 minus, if I plug in -2 to the 4th is 16, divided by 4 is 4, minus, if I look at 2 to the 4th is 16 on 4, yes. And here, I would get 8. And so that gives me positive 4. The area there is 4. Last example was a bit of a thought experiment, pretty much asking how would you find the area between these two curves. Kind of drew something like this, I don't remember exactly, but it's something similar. Then there was another one going through like that. This was your f of x, this was your g of x. First intersection point was A, second intersection point was B, third intersection point was C. And this is the area we cared about. Area bounded between these two curves. So, in general, there are cases in Cal 2 where you have to actually find regions like this, and they won't really give you any of the information, so you'd have to kind of figure out how you put all the information together. So they'll just tell you about one function, f of x, and you'd probably be able to sketch a quick drawing of it, just like I were to sketch this one. And they'll tell you about another function, g of x, and say, find the area between these curves. And basically what you're going to do is you're going to find the intersection points. Those are going to define the limits on your integral, and you want to find all the regions that are bounded between those curves. You would of course ignore the endpoints because these are unbounded regions. That's an infinite area going off there. So that's just a common kind of problem that you'll need to have a handle on. But how would you actually go about finding the area here? As an idea, what would you do? I think that was the last thing. I had a couple more, but they're more of the same. Ideas?
Would you do like the first section plus this, like,
Okay, first section, what are you calling the first section?
I mean, like the
This
integral from like B to A, yeah, or A to B,
Okay.
and then plus the other one, which is B to C.
What would you integrate?
Integrating f of x minus g of x for the first one, and then g of x minus f of x.
Yeah, that's how you do it. It's always top minus bottom. You should be aware that in general, these rules can change. In this region, on the interval AB, your f was on top, the g was on bottom. On the interval BC, this actually flipped. The g is on top, the f is on bottom. So the top minus bottom idea, you have to be aware that in different locations of the problem that you're looking at, you might have to apply you might have different things that you're worried about. And sometimes you can have 2 functions or 3 functions, and then some of them are involved over here and some other ones are involved over here. You have to pay attention, right? That's why sketching is actually a pretty good idea. So sketching is going to be important. When you guys get to multivariable calc, sketching is going to get a little bit of annoying when you have to sketch things in 3D, but it is very much to your advantage that you just bite the bullet, learn how to sketch properly, because then the rest of your life will be a lot easier. Once you can just sketch a nice picture, you can understand where everything is, who's on top, who's on the bottom, who's on the left, who's on the right. Oh, this is relating to that. Spatial awareness is going to become a lot more important. And And of course, you're going to have rules on how you deal with these different spaces. Like what's on top goes here, what's on the left will go over here, blah, blah, blah. And you just kind of fit things into place. And sketching definitely makes things a lot easier than they would be without. Analytical geometry is super useful. We'll take a moment to thank Descartes for coming up with the XY plane. It has certainly made our lives a lot easier. However, we need to get a move on. Moment of silence is over. We're in the end game now. Here's something, recall. We had something called the product rule. So this ends our discussion on the area here. I want to introduce another idea to you guys. So to remind you of what the product rule says, well, it basically said that if you differentiate a product f times g, or f of x times g of x, whatever, then the result will be f prime times g plus f times g prime. Now here's something I want to actually try. Well, the FTC would suggest the following thing can work. I can integrate both sides. Integration distributes across some, so that's what it would look like. And on this side, the integral and derivative actually cancel out. Of course, there's going to be a plus c idea happening here, right? Because the derivative, once you do the integral, there's going to be an arbitrary constant if that comes after. Okay. So you'll get f times g on this side. And over here, we'll have just whatever these integrals will actually be. And for kicks, we're going to solve for this guy. So we have f times g prime is going to be equal to f times g minus the integral f prime times g. So we take the product rule, we integrate both sides of the product rule, we rearrange terms. Now you're never going to really see something like that in your textbook, so let me just change to the notation that they would have used in the textbook. Set let u equals f of x, and let so this means that our du would actually be equal to f prime using differentials. And here's the thing, I am going to set some other function, which I'm going to call let's say v prime equals g prime dx, so that my v would actually be g of x. Right, so I set u equals f, and I set v equals g, and I wrote them in a suggestive way. And so applying these to the let's call it star gives the following kind of rule that we can look at. It says the integral of u dv is equal to u times v minus the integral of v du. And that's the guy that you'll see in your textbook. very common way to express the rule I'm about to give you. This is called the integration by parts formula. Yes, so right now we're in 7.1. It's called integration by parts. And again, because of the fundamental theorem of calculus, we now have the power to reverse all the rules we have from derivatives. Substitution was a reverse of the chain rule, and integration by parts is the reverse of the product rule. And it turns out this is a very useful formula, and we use these to integrate products. So in the same way that you had a rule for derivatives to integrate products, you have a rule for integrals to integrate products. And might as well note here, especially when basic rules and substitution don't work. So again, there's always a hierarchy you should have in your head. I try to apply a basic rule first. Substitution is actually the easiest of the integration techniques that you would know. So if the basic rule doesn't work, you're going to try to get substitution to work. That's always going to be the second thought you're going to have. The third thought might be something like integration by parts. As far as integration rules go, this one is also kind of simplistic. So this will probably be the third thing you're thinking about. And this is how it's done. It's the integration by parts formula. Why is it called integration by parts? Well, because you choose parts. You call one part of your integral the u, you call the other part the dv, and these two parts together gives you this formula. You can, I don't know, fine. I don't really have a nice mnemonic for this one like you had for the quotient rule. I used to have a friend that said video in his mind to remember that there's a VD over here. I don't know. However you can memorize it, memorize it. That's the integration by parts formula. Okay? And so how it works is in the beginning you will choose the parts. You're going to choose the u and the dv, and then the formula will unfold this way. And in theory, when this guy works is that this is the integral you want to compute. However, this integral would be easier to compute. So you don't really know how to do this, but you would, in theory, know how to do that one. You might say, well, why would that necessarily be easier? The one over here be easier? Well, let's actually do an example. Well, you should, at least in part, be able to see how it could be easier. Imagine if your u were a polynomial, like an x cubed. On this side, you'd have an x squared, right? You'd automatically be breaking down a power, right? So there are times when, instead of thinking of a function, thinking of its derivative can make things easier, right? You break down the powers, right? This guy could be an ln x, whereas over here, it's a 1 over x. It's an x to the minus 1, right? So a lot of times by doing this manipulation, you can actually obtain an easier integral in order to figure out a harder integral that you care about. And usually you'll have a product in which you can do this. You have two functions being multiplied where you can think of one as a u and one as a dv and go through this procedure. So, idea. To perform int by parts, course, you're going to want, you first make that choice. Choose your U and dV. You're going to, no pun intended, derive du and v. Right? Not like differential, just regular, just find them. Compute. That automatically will give you some sort of restrictions start popping up in your head. Obviously, u should be something you can differentiate easily, whereas the dv should be something you can integrate easily. So if there's something that you don't know how to integrate, you're never going to choose that as your dv, right? In most circumstances. And three, you're going to plug into the formula. Let's start with an easy example. xe to the x. Does anyone know off the top of their head what you have to differentiate to get xe to the x? Well, that's kind of weird, isn't it? Let's actually figure it out. So here, one thing I noticed, I have an integral. Could a substitution work here? What would you substitute? U equals x is always a bad substitution, so obviously not that. Talking about u equals e to the x, probably going to get an ln into the mix. But does anyone know what the integral of ln is? Huh?
Is it mod x?
No, that's the derivative. The derivative of ln x is 1 over x. What is the integral? The antiderivative. We're going to see today. So we don't know that. Substitution is not going to work here. Obviously, a basic rule doesn't work. However, I do see that we have a product here. What are you saying?
So why do you ask if you know we don't know?
Because it's important. Because thinking 1 over x is the answer is a common thing, and I want you guys to understand that that is a thought you would have, and now you can tell yourself, that's definitely wrong, never think that. That's important. The thing is, if I never asked, you guys probably would never know you had that misunderstanding, and then you'd go on a test and you'd apply that misunderstanding. It's important to speak. Even if you're wrong, it's important, because knowing that you're wrong before you actually need to know you're wrong is a super important thing. It's better you get something wrong now than get it wrong on the test a week from now. You understand what I'm saying? Well, I mean, I know the semester is almost over, but hopefully that was clear. I don't expect you guys to speak when you think you're right. I want you guys to say regardless. Even if you're wrong, it's important that we all know you're wrong. I need to know, okay, the class has this misunderstanding. I should probably say something about it. And then you would know, oh, I had that misunderstanding. I should probably clear that up in my head. Right? No matter what, you should speak. Even if you're wrong, it's very important. Don't be afraid to fail, especially when there are no consequences for it. Like there are no consequences for it just now. Okay. So the idea is substitution won't work, basic rule won't work, but it's a product, so I'm going to think, okay, integration by parts. Now, how could this be easier? Well, I do realize that if I were to differentiate x, I would have 1. That will probably make things easier, so let u be x. And then my dv will be e to the x dx. So I'm going to look at these guys and I'm going to choose one part to be the u and this part to be the dv. Right?
Didn't you say not to pick u as x?
Huh?
Didn't you say not to
For substitution. I'm not
for
doing substitution.
Oh, okay.
I'm doing integration by parts.
Okay, okay.
Yeah. When it comes to substitution, u equals x is always a bad idea. For integration by parts, it's a completely different animal. Different set of rules work here. And I'm going to tell you the things you want to keep in mind for this rule. Okay? So the u equals x is just a coincidental notation. It's not a substitution, really. So now your du would be, of course, 1 dx. What would the v be? What's the integral of e to the x?
E to the x.
Well, it's e to the x. You can ignore the plus c, we'll throw that on there. And so now we have a formula. We know that the integral of u dv is u times v minus the integral of u. Right? So that means this guy is going to be equal to my u times the v minus the integral of the v times the du. So that's what this guy is. And now, lo and behold, that integral is a lot easier. We have a basic rule that works on that integral. That's the integral. You might also write this as, I wouldn't care in general, but something like that is also, you can factor out the common e, whatever. But that's the antiderivative. If you differentiate this guy, you will get the other one. To differentiate this, you'd use the product rule. Differentiate the x, you'll have e to the x, plus you differentiate the e to the x, leave the x, you get x e to the x. Then the derivative of minus e to the x will be itself. That minus e to the x is going to cancel the other e to the x from the first differentiation, and then you'll end up with x e to the x left over. And that is integration by parts. Now, here, I mean, if you really think about what you're aiming at, trying to get an easier integral, it was almost obvious that x was the choice I should have made here, but in general, it's not going to be obvious, so now I'm going to tell you how to choose. There's a mnemonic, of course. It is called liate, because you can line things up. Usually you imagine it vertically. Now, liate stands for logarithms, inverse functions, like your inverse trig functions, etc. Tan inverse, sine inverse. A stands for algebraic, which is a very poor choice of terms, but I think lipte would be sound weird to people, but algebraic really means polynomials in this case. In general it doesn't, but in this case it means polynomial. T stands for trig functions. And E stands for exponentials. And here's how the rule works. The guys higher in the list get to be u first. And as you go down to the list, these guys get to be u last. So if you have a product of these two types of different functions, your choices will be clear in the sense that you will always choose based on this mnemonic. You will notice in this example, my x falls in the A category, while my e to the x falls in the E category. So, according to Liate, the A gets to be the U before the E. So I would choose U to be this. So if I have a multiplication of an A and an E, the A is the U, and that guy's the DV, right? If I have a multiplication of an I and a T, this is the U, that's the DV, right? So the guys higher in this list get to be the U. And that's how you choose. That will always get you to an easier integral, quote unquote. So that's how you choose. So here, seeing xe to the x, I'll realize, okay, a basic rule doesn't work, substitution doesn't work. And therefore, I will try integration by parts. That might work, provided I get an easier integral. Knowing that I'm going to do integration by parts, who gets to be the u? Well, I think of Liate, and the x gets to be the u. So that is how you choose the u versus the dv. Yeah.
If you're, like, if you don't have to do this, but you just like automatically jump to it because you're on a test rushing, will it still like work out?
In what way? What do you mean?
Like the one we did earlier today where you could, well, that's a stupid example, but like, if substitution could work, but you jump right to integration by parts, will you get the right answer with integration by parts?
If it works out, yeah.
Yeah, okay,
Yeah. Like, you'll always get the answer.
okay.
Once a method works, it'll give you the answer. It's just that one might be more efficient than the other one.
Okay.
So I would say it's not just like this won't work and that will. It's more of, you know, this will be easier for it to work than that one.
So like, what are the cases where substitution works, but this does not?
Well,
I guess like this one, like, you know,
like that one.
makes sense.
Why? Because if this is your dv, good luck.
Yeah.
There's no integral for that. It'll be impossible to find the b. But that's easy to do by substitution.
Right.
U equals x squared.
You would get stuck right away if you tried
Yes,
this.
you would get stuck if you tried this.
Okay, makes sense.
But again, you still want to think of the easiest way to get around something, as opposed to the hard way, in general. And as a, you start, when you learn a bunch of integration techniques, you'll start to realize, like, through practicing a bunch of problems, you know, it's easier to apply this technique than that one. And yeah, besides the basic rule, substitution is the easiest technique out there. Integration by parts is also pretty easy. Right? You start doing like trig substitution, and you start realizing, oh yeah, this is pretty annoying. So, yeah. So, integration by parts, another technique. This is how you choose the parts. And again, in general, there'll be other hints to you, but in general, this would be probably around the third or fourth thing I would think about doing when faced with a random integral. I always try to get the basic rules to work out first. Let's actually talk about this guy. This reminds me of in my 1203 class, when before I told them the rule for doing that, I asked them, what do you guys think the derivative of this is? Obviously they tried to apply the power rule, you know. That gave me an excuse to give them that speech about, you know, the variable has to be in the base, and this has to be in the power, and your attention to detail. You need reminders like this. Let's actually get the integral. We know how to find the derivative of this. We don't know how to find the integral. Now, we don't have a basic rule for this, at least I didn't tell you. However, I will say, now, once I derive this for you, I want it to become one of your new basic rules. Once we derive the integral of ln x, this should now be something you just know forever. Okay, that's what the integral of ln x is. But we're actually going to derive it with integration by parts. Okay. So, we don't have a basic rule, so that's out. Can't simplify it to look like a basic rule, really, so that's gone. Substitution, where are we going to substitute? This thing doesn't even have two parts, so we want to do integration by parts. Now you're going to run into the thing of, well, what are the parts? There's only one function here. Well, not really. Remember the integration by parts had the dx in one of the things. those are the parts. I can actually think of this as two parts. If it makes you feel it better, you can think of this as ln x times 1 dx. So that can work. You can create another part by using the number 1. And so that 1 is a polynomial. So that's an a. ln is a logarithm. That's an L. According to Liate, that guy gets to be the u, which is kind of obvious because you don't know how to integrate it, so it could never be the dv at this point. The du is of course going to be 1 over x dx. And if my dv is 1 dx, my v is going to be x. And so now I'm going to plug into the formula. I want u times v minus the integral of v du. U times v, so that gives me x ln x, minus the integral of v times du. Well, that's just 1. We know how to integrate 1. So that's going to be your integral. In other words, the integral of ln x is x ln x minus x. And I pretty much remember that from now on. This guy is now inducted into the basic rules category because the natural log is a very basic function to us. It's one of our building block functions. So now a basic rule. That's how you integrate something like ln x. And of course, you're free to check this. You can differentiate the right side, differentiating the first term using the product rule, second term using the power rule, combining terms, you realize ln x is what survives. So I'm going to want to show you a trick with this, but that will be for next time. Let's do another example. Say I wanted to integrate the inverse sine function. I could do a similar trick. I can think of this as this times 1. So now I would choose my parts. Liate, the I comes before the A. This would be an I, that would be an A. So I would choose sine inverse as my u, which again, kind of makes sense when you think about it. I don't know how to integrate it, so obviously it's going to be the part that I differentiate. And I'm going to make my dv equals 1 dx. So my v is also going to be x. What's the derivative of sine inverse?
1 over the square root of x squared.
So this guy would become u times v minus the integral of v du. How would you integrate that? Ideas on how to integrate this. Substitution. So here you do a substitution. So again, just as when we were doing derivatives, we realized sometimes we have to use several rules at a time. I can start out by using the product rule, but then I realize I have to use the chain rule over here or something like that. Once you start learning integration techniques, you might have to use several at a time, and that's fine. So the substitution here would be u equals 1 minus x squared, not to be confused with that u. Your du would be minus 2x dx, so your dx would be du over minus 2x. And so this would become x sine inverse of x minus, well now it would become plus 1/2 times u to the minus 1/2. Add 1 to the power, you get u to the 1/2. Divide by the new power, you get 2. And so this is actually just x sine inverse x plus, these cancel, it will just be the square root of 1 minus x squared. Exactly. And of course you can differentiate that and see that you'll actually get the original. Another example here. This guy is an A, that guy is an L, according to Leate, integration by parts. This would give us x cubed over 3. Plugging into the formula, u times v minus the integral of v times du. That one I can integrate pretty easily. That will be it. As a segue into our next lecture, consider the following. Think about how you do that one. Or maybe even try it. And it's going to give us reason to develop a new technique, which is pretty much integration by parts, but you kind of make it more streamlined, and it's called tabular integration. So we'll stop there for now. See you guys on Tuesday.